All right, so now let's take a look at problem 15. So suppose that circles of equal diameter are packed tightly in n rows inside an equilateral triangle. And the figure illustrates the case n equals to 4. So there's 4 rows. 1, 2, 3, 4. Notice how they get bigger and bigger. You start off with 1, 2, 3. So if you have the fifth one, will be at 6. Actually, yeah, it will be 5. Yeah, I mean, we'll have 5 balls on the fifth one, 6 and 6 ones, etc. So notice that's the perfect triangle set up there. And you can see the equilateral triangle because there's 4 on this side, 4 on this side, 4 on this side. So if A is the area, so here, this is case n equals 4. So if A is the area of the triangle and AN is the total area occupied by the n rows of circles, show that the limit as n approaches infinity of an divided by a equals to pi over 2 times square root of 3. So again, an is a total area. A is the area of the triangle. So an is the total area by the n circles. So this is an. So all that together is an. This, yes. And then the total one of the triangle is just a. All right. All right, so now let's take a look at the solution. So if L is the length of a side of the equilateral triangle, then the area is, and again, recall equilateral triangle, just write it out for completeness. This becomes like this, and let's put this better. All right, so we have a triangle, side lengths are L, and we have this height here. This height is H, and then the base is B equals to L. So it's all the same. And over here, this from here to here is L over 2. So again, recall Pythagoras. We have L squared equals to H squared plus L over 2 squared, which equals 2H squared plus L squared over 4. And then move this over to the other side and then all the way to the end. And then square root, we'll get H equals to plus or minus square root L squared minus L squared over 4. Again, this is 4 over 4 times 4 over 4. This just becomes, again, only take the positive because we're dealing with this. But I always put that just because technically it is plus or minus on the square root. So what we'll have is square root L squared. If this 4 minus 1, 4 minus 1 is 3. So we'll have 3L squared over 4, like that, over 4. And then square everything in there. This becomes square root 3 over, and then this is a 4 there. Yeah, square root 3 over 2 is 4, square root 4 is 2. And let's put this over the whole thing. Then L squared, square root of that is L. Like that. All right, so this is our H. And then recall the area is just equal to base times height divided by 2. So base is equal to L. So we'll have L times it by H square root 3 over 2 times L. And then divide this all by 2. And this equals to, well, we'll have a L. This is going to be square root 3 is by itself, and then add 2 into 2 becomes 4. Then we have an L squared like this. All right, so this is a. I'll just put this equals to A like this. And since we're asked to find the ratio AN over A, well, let's just write L squared as A. So this is and L squared equals to 4 over square root 3. So move everything over to the other side, move it there, etc. So we'll get a 4 over square root 3a. So that is what L squared is equal to. So we have that a as part of L squared. All right, so now let's take a look at the circles. So let R be the radius of one of the circles. When there are n rows of circles, the figure shows that. So if you have this figure like this, so this distance from here to here is R, and then what we have is from here to here is also R. So it's all radius. So in other words, from here to here is r. And then continuing over here, this is going to be 2r now. Now we'll have it as 2r. Let's put it here, 2r. And then keep going further. There's another 2r. So that's just a diameter. And then we have an r. Like that. And then this is at the center here. And now we have a point. And then we can draw a line like this. I'm going to draw it like this. So the idea is we want to get, so that's 2r there. Now we want to get this distance across here. So this distance and so on. And this one here. It's going to be the same. And notice that, well, if this is r, so this height is r, and this right here, so this equilateral triangle, so that means is this angle, this is pi over 3 or 60 degrees. So then this right here, you're dividing this in half. Again, it's all everything's symmetric. So this one has to be right here. This is pi over 6, and then we can it's just pi over 6. So then what this means is, well, if we have pi over 6, so recall the triangle. Equilateral triangle looks like this. So we have this. I'll put this here. So we have this. All right. So if we have this is all pi over 3 angle, like that. This is pi over 3, and then if we cut this in half, I'll just draw this a bigger line. Cut this like that, a thicker line. So this is going to be, and if this is pi over 6, and if this is r, so this is this part here, then this this hypotenuse is 2r, because it's all the same. So this is r. So in other words, this has to be the same. So this full length is 2r. And it's all equilateral, so this is 2r, like that. So in other words, if this right here is 2r. And same for here, this is 2r, like that. And thus we can calculate this right here. This is our height, or I'll call it lowercase a. So that's our a. And we could just solve that. And again, a is equal to plus or minus square root. And we're just going to take the plus. Again, I always do the plus minus just for completeness. So then the hypotenuse squared minus the base right there, or the adjacent. Well, it depends on where the angle, just that side r. So I'm going to move this better like that, this like this, and this like that. So just minus r squared, like that. So a is equal to, a is equal to, in other words, 4r squared minus r squared, which equals to, this just equals to 4, so square root 3 actually. So it's going to be, well, before that, this becomes 3r squared, and this equals 2 square root 3r, like that. So that is our a. So we know that that full length is there. So now we can solve this. This a is equal to square root 3 over r. So we'll square root 3 by itself, and then times it by r. And similarly on this side here, square root 3 times by r, like that. So then the full length of the side in terms of r, so in terms of r, so this whole height, or this whole length is L. So we have L. Alright, so we have here, so this is for n equals to 4. So what we have is, thus, I'll just put first L4 is equal to, for the n, for n is 4. I'll just put that instead here. So 4, for n equals to 4, we have L is equal to, square root 3, square root 3 times r plus, and then what we have is an r plus 2r, r plus 2r, plus 2r times, I'll just put this as, plus 2 times 2r, and then plus r, or I'll just put this all together actually. So plus r, 2r plus 2r plus r, and then plus the last one, a, is square root 3 over. square root 3r, like that. And in fact, yeah, so the only key part that we need to worry about is this part, or just to analyze further. So this part here could be written as 4 minus 2r, which equals to 2 times it by 2r. 4 minus 2 times 2r, yeah, which equals to, in this case, 2 times 2r, like that, which equals to 4r. So that's for n equals to 4. So for, just for general, for n, yeah, in general, like this, so for Rn in general, yeah, this is going to equal, L equals 2. Well, we have the square root 3 times R, and then these just add up. You could just add those up. It doesn't change anything there. But just for completeness, I'm going to write that. So we're going to have this segment. So square root 3r plus, then we always have this additional r. Before we have this, all these two r's. Plus r, and then plus here, this is 4 minus 2. In other words, that was n is 4. And this keeps going on. And then, so the next one for n equals to 5, we're going to have 3 of these. So in other words, we'll have a 5 minus 2. So what we'll have is, this could be as, yeah, this will be n minus 2. So for n is 5, we'll get 5 minus 2 is equals 3. Yeah, so we'll have 3 of these big circles inside there for n equals 5. Yeah, so n minus 2 times it by 2r. So plus r, and then the last segment is this plus r, and then times square root 3 over r. Like that. And now, yeah, so that's 2r. So now we can just combine all the like terms. So this becomes equals to 2 square root 3r plus 2r, and then plus, yeah, plus, well, this one we can just multiply this inside there, and here. So this becomes plus 2 nr, and then minus 4r. Like that. Yes, that's what we have. And now what we'll do is we'll add these two together, and that becomes, well, minus 2r, and also factor out the r. So r times it by 2 square root 3, and that becomes right here. We'll first put the 2nr. Or actually, put this first. I'll put this one first. And then this will be 2, yeah, we're factoring out, yeah, 2n. And then we're going to factor out the r. So plus, and the next one is 2 square root 3. And then this one here, combining these two, these would be negative 2r. Like, I mean, it will be factor out the r. So negative r, negative 2, like that. And now this equals 2, factor out the 2 now. So 2r times by n plus square root 3 minus 1, like that. And now this whole thing equals to L. Remember, this whole thing, this was just our length L. So now if we solve for this R, so we'll have to divide this out, move it over, and the 2 move it over. So what we get is R is equal to, and this will be L, yeah, so L over 2 times n plus square root 3 minus 1, like that. Alright, so thus we have here, and just added the word thus, we have r equals to all this. Alright, L equals to L divided by 2 times n plus square root 3 minus 1. So that's what we have for r. Alright, now that we have the radius of each circle in terms of L, we could solve the area for it, but first let's count the number of circles. So the number of circles is, I'll put this number equals 2. Well, for n equals to 4, we have 1 plus 2 plus 3 plus 4. So yeah, we have, well, 1 plus 2 plus 3 plus 4. And again, for n amount, we're going to go plus dot 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 all the way to n. And this just equals to, well, the sum of integers. This is the sum from I equals 1 up to n of I. So sum of positive integers. This just equals to, well, n times n plus 1 as per my earlier video. So that's the number of circles. And here for n equals 4, we'll have 4 times 5 divided by 2. Well, that'll just be 10. And we can count that here. So this can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and yes. And yeah, so here, recall this formula. So recall that the above formula is for the sum of positive integers. Let's write positive integers, which I went over in my earlier video. So here's a link to my earlier video. So a summation from n equals 1 to n, from I equals 1 up to n of I equals 1 plus 2 plus 3 plus, etc. all the way to n equals to n times n plus 1 divided by 2. All right, so then we can calculate the total area. So thus, the total area of the circles is, and we'll call this AN. So this is going to be A sub n. This equals to the total number of circles, n times n plus 1 over 2 times it by pi r squared. So area of a circle, pi r squared. And this equals to, well, we're going to write this in terms of L. Remember, we want the ratio of AN over N. So this is what we want, AN over AN over A. And we know that L squared is in terms of A there. And we can write this whole formula AN in terms of L because we know R is in terms of L there. So this equals to, I'll move the pi in front, or we'll move it after actually, just to show where the R fits in. So over 2 times pi, and then times it by this formula right here, L over 2, and then n times n plus square root of 3 minus 1. So over L, and then we have a 2, but then we're going to be squaring it. So this, but then since we're squaring it, we'll put a square on every single one, and 2 squared is going to be 4. So this becomes 4 times by n plus square root 3 minus 1, and then squared. And now before going any further, well, notice there's an L squared there. So we have this L squared, and well, we know that L squared, we wrote that earlier in terms of A. So L squared equals 4 over square root 3 times A. And again, we were asked to find the limit as n approaches infinity of AN over A. So we could replace this L with A. Yeah, so this will be 4 times square root 3 times A. So this equals 2, and let's put this all together. Well, let's keep it as is, n plus 1 over n, over 2, times by pi, times this by, and this was 4 over square root 3. This is our, let's see if I remember that. Again, so 4 over square root 3 times A, like that. Yeah, times A. And that is going to be, again, times this all by, times by 1 over 4. And again, this is our L. I'll just circle that so that they line up. And then n square root 3 minus 1 all squared. And I'll extend this. And now we'll do some cancellation. So this 4 cancels with this. And we're left with, and let's just do some simplification. So this equals 2. We'll put the pi in front, and we'll multiply this inside. And then we'll do that in a bit. So we'll have pi right here. So pi, and actually before I even do that, I'm going to take this A, I'm going to divide this out so that we get AN, just make it simpler. So AN over A is equal to, and then there's the pi over 2 square root 3. So we got rid of this. So we have this, this, and this. The next one is this multiplies inside, and this 4 is gone. And then this becomes like this. Make the n's by themselves. So n squared plus n over n plus square root 3 minus 1 over 2. And now since we're going to take the limit, we want to multiply top and bottom by n, because otherwise we'll have an infinity over infinity. So multiply top and bottom by by 1 over n squared, like this, divided by 1 over n squared. So then that means we can put this inside this squared square power, because the same, that'll be the same power. And then this equals to, let's put this all over here, equals to pi over 2 square root 3. At 2 square root 3 times it by, this will be n. Actually, no, n squared divided by n cancels. So we'll have 1 plus, and then 1 over n, because this will be cancel out with this. And we're left with, at the bottom, it's going to be this 1, because then when you divide this out, we'll just divide by n inside this square, plus square root 3 minus 1 over n, like that. Let's put it like that. All right, and now we can take the limit. Yeah, so we can take the limit, so thus the limit as n approaches infinity of the ratio an over a, and just move this a bit to the bottom. So thus, move this here, equals to the limit as n approaches infinity, or actually instead of the limit in front, put the pi 2 over square root 3, the constant, out of the limit, so n approaches infinity of 1 plus 1 over n over, right here, 1 plus square root 3 over 1, and this is all squared, over n squared, like that. And now as you plug in infinity, we'll get this 1 over infinity goes to 0. Similarly over here, this becomes 1 over infinity goes to 0. So it's, it goes to 0, like that. So in other words, this whole thing is equal to pi divided by square root 2 over 3 times by 1 plus 0. 1 plus 0 over 1 plus 0 squared. So in other words, this whole thing just goes to 0 right there. So it's multiplied like that. And this all just becomes 1 over 1. Yeah, that becomes just 1 over 1 there. So 1 plus 0 is just 1. Yeah, so in other words, this all just cancels. It goes to 1. So what we get is limit as n approaches infinity of an over a equals to pi over 2 square root 3. And this is exactly what we were asked to solve. And we can go scroll up to see our question. And yeah, so it says show that limit as n approaches infinity of an over a equals to pi divided by 2 square root 3. And that's exactly what we just showed.